Yeah, hello friends. How are you? With the hope that you do fine. Welcome back again to this channel. Uh, we love speaking about architecture. We love speaking about engineering and also construction. Well, I thought of coming back again and doing a video, a quick one about a very interesting topic. And today I thought of speaking about stiffeners. If you're a steel designer or you're a student studying steel design, then you must have come across the term stiffeners, in steel. And we want to just do a quick overview, of what stiffeners are, just the basics, zero mathematics, so that we have the real knowledge of how stiffeners work and what they really are. Then from there, I think one can take a step forward and start doing the mathematics, after understanding the concept of what stiffeners really are. Well, I was browsing through the internet, and I got some good pictures which can help us illustrate what they really are. So if you look at this one, I got this picture from this website here. You can just follow through and read a lot about it. And if you can see, this is a column. There's a column here sitting on a base plate. This is a base plate, and there are some steel members, some steel plates, which are welded, onto the column and also the base plate, right? So these are exactly what we call stiffeners. These are what we call stiffeners. So these are stiffener. These are stiffener. The stiffener. These are what we call stiffeners. If somebody is wondering what they really are and what they really do, I think this is the video for you. So that is a stiffener. I also had another video, this one here, another stiffener here. So these are called base plate stiffeners because they stiffen the base plate. We'll just come to that in a short while. There's a stiffener here. It is welded onto the column and also the base plate here. There is also another stiffener. This one here, it is welded onto the column. So these are column stiffeners. This one here, it is stiffening the web here, but why should we add them? We're going to see that in a short while, right? There is also a stiffener here welded onto this column or onto this web. So maybe the final one, we also have a stiffener here. We also have stiffeners here. There's a stiffener, there's a stiffener. They're welded onto this web, the web of this girder here, and therefore we really need to understand what are they and at what point do we really need them. Yeah. Well, so maybe if we go back to first picture here, how the base plate works is that when you have a column, I'll do a sketch for that, and this is a base plate. This is a base plate, and you have a column. Then there is a load which is coming down this column, say P. Well, what happens is that there will be reaction at the bottom of this, of this base plate, right? A reaction from the support below, the bottom of this base plate, and that reaction will cause bending. Will cause bending in this base plate here. So this base plate will bend and become something like this, right? Because of that load which is coming, because of that reaction which is coming from the bottom. So this is what we expect. So it will behave like a double cantilever. It will behave like a double cantilever. We have a cantilever this side, and we also have a cantilever this side with a distributed load. The distributed load at the surface here. So what exactly will happen? If we draw a bending moment diagram for this, this is the column. This is the column, and this is the base plate. If you draw a bending moment diagram, then you're going to have something like this. That is the bending moment diagram. Obviously it's going to be something parabolic, but for simplicity of design, we just do a linear, curve. Just do a linear curve. So this is how the moment diagram will look like. This is how the bending moment diagram will look like for this one. So that means we have very high bending moments at this point. At the edge here, we have very high bending moments, the edge of the column here. So this is just a cantilever which is supported by this column, right? So that it bends like this, it also bends like this, So we have very high bending moments, But if you have to design for this bending moment here, then let me just delete this. Let me just erase this. If you need to design for this bending moment, here, because this is the maximum bending moment, and that means you have to design your base plate to take that bending moment, which is very high. That means you'll require a very thick base plate, which at the end of the day is very expensive. Very expensive, and also very it takes time to be done, right? So designing is just balancing the economic side of it and also the engineering bit of it. So instead of having a very thick base plate, which is very hard to do, what we do is we add these stiffeners here. So this stiffness will take that bending moment, and if keen enough, you'll realize that our stiffeners are taking the shape of the bending moment diagram here. If you look at the stiffener here, it takes the shape of that bending moment diagram, with the high bending moment at this point, right? Yeah, and the bending moment reduces as we come down. That means you don't really need very much area at this point, because there is a very little bending moment at that point, right? So that exactly is why we need stiffeners at the base plate, so that we don't have excessively very thick base plates, right? Because we can just do a very small base plate. Obviously you have to check that through design, and after that we just add stiffeners. So what will happen here, after adding stiffeners, we'll have so in this case we'll have some kind of supports. So we have a support here for this base plate. Look at this base plate here. It is now supported here, and it is also supported here. That means that the effective length is now reduced, right? Now take for example, you want to draw bending moment diagram for this one now. So compare if you don't have a stiffener and if you have a stiffener. If you have a stiffener, then the bending moment diagram will obviously be something very the bending moments will be so small, right? That means that bending moment cannot be carried by the plates, right? Yeah, but then if you don't have if you really do not have the stiffeners, that means you have to design for very thick base plate. The same case for this photo here. If you look at this stiffener here is added to stiffen. It is added to stiffen this base plate, so that it doesn't yield because of the excess bending moments. So that is literally the idea about the base plate stiffeners. So we have the base plate stiffeners, and we also have the web stiffeners. Well, that is a very good explanation for the base plate stiffeners. We can check again the web stiffeners. If you look at this one here, let me just do Yeah, so this is a web stiffener. And how does it work? You know, if you load this, let us load this beam here. This is a beam which is attached to a column. So let us load this beam. If you apply a point load at this point, what will happen to this beam here? This flange will be in tension, right? And this flange here will be in compression, right? I hope we understand that. If you apply a point load at this point, that will set this member into bending, and if it is bending, then this top flange will be in tension and this bottom flange will be in compression, right? So what happens is that that is the depth of your section, and you have force at this point. Actually, you have a moment, because the distance from the centroid of your member to where the load is applied will give you a moment. So that is an external moment, right? That external moment will cause the internal moment in this member. So if you take this force, you multiply by the lever arm. Lever arm is just the distance between these forces. This is the tensile force, this is the compressive force. So this is the lever arm. So if you take this, you multiply by this force, you will just get the moment, which is force times distance, right? Well, that means if the moment we have this moment here, then we can get both the tensile force and we can also get the compressive force, because we know the distance here. So after that, that means we are now applying in this column, we are applying a tensile force. In this column here, we are applying a tensile force at this point. Yeah. Then at this point, we are applying a compressive force. We are applying a compressive force. What will that do? That will cause some kind of, that will stress our web here very extremely, because if you look at if this is a web, let me just draw a steel, let me just draw an elevation of a steel section here, and so these are web, these are flanges, these are flanges, these are flanges. So these are flanges, this is a flange, I've just drawn the, I can also do a section that will make it look more. So we have a section here, this is steel section. So this is just elevation through it, right? As we look at it from this side, this is just elevation through it. And then you apply a point load at this point. If you apply a point load at this point load will just be carried by some part of this web here. This point load will not be carried by the entire web. So this point load, the way it will be distributed, so if we have maybe a silo, or we have a secondary beam sitting on this primary beam, then what will happen is that that load will be distributed like this, right? That means at this point in our web, the area which will be carrying that load is just some area specified by the code, right? That is specified by the code. You can get that from the code. That means that this is the only area which is carrying that point load from top, right? That is the only area which is carrying that point load. And what will happen if that is the only area carrying that point load? This web, it can buckle, or it can cripple. It can also crash, right? So buckling is where you just have Buckling is where you have this web, it bends out of plane. You can use another color for that. It bends out of plane before yielding, right? The entire web buckles out before yielding because of this concentrated load here, you know. And if you speak of this web buckling, if you speak of web crashing or web yielding, it's very simple. You just have a web, just have a section, but this section will just fail at some point here. It will just crash. Yeah, that means to yield. That means the material of the web has reached the yielding point, right? So what you have to do is to make sure that you design that web to be able to carry that load, right? We also have localized failure, where you just have a section of this web buckling. You know, it's called local buckling of the web. So you have to really check your web. If your web is not sufficient, then you have to make sure that you provide stiffness. So that is where stiffness comes in. So the reason as to why I was explaining this is to bring that point just right here, that this force which is here will just be carried by some part of this web, right? And this part of the web can buckle. It can buckle out, it can crash, you know, or it can cripple. So what we need to do is that we ensure we do the check, and we ensure that that web can really carry that load. If it can't carry that load, then we provide stiffeners. So these are the stiffeners. So stiffeners are meant to stop this web from buckling. So if you provide a stiffener here, this is a stiffener. I also provide a stiffener here. Then this section of the web will not experience local buckling or the global buckling of the web. So that is entirely how it works. If you understand that, you'll be good to go. So just make sure that if you're designing for this point load, make sure that you check for all of them. You first have to check for the entire buckling of the web, and then you have to check for the local buckling of the web, and then obviously you have to check for crashing, you know. And if it is not sufficient, then you have to provide your stiffeners to take care of that. Well, I think there is a mistake which people usually do. Let me just explain that. A mistake which most of the designers do. You know, if you have, what most of the designers do, which I feel is a mistake, is that if you have a section, here, and you apply a point load, this is the elevation of the section. These are flanges. And you apply a point load. So maybe we have a support here, and you also have a support here. So the mistake which you should be really very keen about is, because if you do the shear force diagram here, it's going to look something like this. We have that point up to there, and then this, the shear force diagram. So you find most of the time designers just take this maximum shear force, and that is what they design for. But that is very unfortunate, because you have to check for this point load here. You have to check for the effect of that point load in that member. Yeah, and you have to check for it at a distance away from the edges where the point load is being applied in. Well, that is just the same thing with this one here. If you have point loads now, so you have point loads which are coming down. You have point loads which are coming down this girder here, and you realize that your web cannot take them. Then what you do is just providing your stiffeners, just providing your stiffeners to take care of that those excessive loads. So I think a good take home is that maybe from the very first slide, this is for the base plate. You provide stiffeners to take care of the base plate so that it doesn't get very expensive, right? And that is what I was trying to illustrate in this slide here, in this page. The same thing here, and then was explained that using this, and we've seen that for us to provide stiffeners, then you have to check for web buckling, web crippling, and also crashing of the web. If it is not sufficient, then we do provide our stiffeners here. I think that is enough for today. Just in case there are questions about the same, about stiffness, you're free to ask them in the comment section, so that when I go through, I will get an opportunity to respond to them. Otherwise, if you like seeing the same, you can always show the friends. You can also subscribe so that you don't miss the next lectures. We'll be tackling these topics one by one, so that we be good engineers, right? Share ideas so that we be good engineers. Thank you for keeping with me to the end. We shall meet another day. Bye.